the famous videographer. How long has your dad been in Norway?
Oh my gosh, yeah. Last Friday.
Okay.
A week. Yeah. But then he's going from there to Seattle to my sister and her dorm, and then he's going back here.
Okay.
But yes, it was like 1 a.m.
Yeah, so I went to Twissy's first period, and your dad was saying it was late, so when he came to this class, I'm like, I suppose it's even later now.
Yes. Yeah. He went to go inside like 1 a.m. instead of, and still like ask forward for questions.
Your parents, oh no, your parents had no questions. Your parents were nice. Second period, lots of questions. Only people who had questions.
Back to school. No one was there.
Okay, so speaking to Emma's point, we're kind of building on what we did last class, and we're also going to talk about isomers today. So I totally lied to Quinn. Sucks to suck. Quinn is at the University of Rochester. That's where my dad went to school. I don't know where the rest are. So I'm thinking about 2-bromobutane. So if I drew that picture for you, and I just focused on kind of the carbon of interest, I think that should look like 2-bromobutane. So I have the butane chain running from left to right. On the second carbon, I have a bromine and a hydrogen, and then I have the methyl group and the ethyl group. I've drawn it this way because I want you to see that we have a carbon that's bonded to 4 different things. And so this carbon is a chiral carbon, because that's our definition of how we figure out something's chiral, right? She didn't bring donuts for the whole class, but it looks like she brought them for herself. And I'm going to react this with some hydroxide. And I know in your most recent assignment you were asked to talk about some dipole moments. So where is the dipole moment in 2-bromobutane? So the bromine is negative, the carbon is positive, so the dipole is right here. With bueno? Take it. And so if you were a hydroxide, a nucleophile with a lone pair of electrons and a negative charge, how do you think you would approach this molecule? Where would the hydroxide be most likely to go? It's going to attack the positive carbon. Is it going to attack here? 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 Channeling my inner current. As a hydroxide, what would you hate most, Mohab? Another negative charge. The most negative charge in this thing is bromine. And so what we find is that the hydroxide does quote-unquote backside attack. So with Rita and the ridiculousness of boys, you can imagine that this is going to be funny in the other class, but for you, we're just going to come in on the opposite side of the leaving group. So what Brecken told me is that it wants to find this positive carbon, but the thing it hates most is this bromine. So it's going to approach as far away from the bromine as possible to that positive carbon. And so when I draw the 5-member transition state, I'd like to think about what the 3-dimensional shape might look like. So this hydroxide is going to start coming in this way, and then these 3 groups are going to kind of be in the way because it's a tetrahedron, so they're pointed down in my picture. You feel the down or not so much? We've hit total silence.
I don't know. I believe in it.
Where's the down?
Like different molecules and
Yes?
will it make different like molecules depending on where it goes?
we're gonna see why it's important that it does this backside attack. It's known as Walden inversion if you want another name for it. I mean, I know this is a pretty crap piece of a tetrahedron, but you know, it's the fastest thing I could make. So we're taking this molecule and it's coming in from the back. And I'm saying these three groups that are down, what are they gonna do to make room for this bromine? They're gonna come out. I think of this as a weird umbrella. So right now my umbrella is like this, and I think the transition state, I'm gonna get a shape I actually know. Isn't that interesting? I'm gonna get a shape where the bromine bond starts to break, the hydroxyl bond starts to form, and I have something that looks like this actually. So we've never tried to draw this in 3D, but you know, today was the day I thought we would. Does anyone recognize that shape? It is the transition state, but it's one of the best for shapes we learned in 14.1. Trigonal bipyramidal, trigonal bipyramidal, like you can pronounce any way you want, I don't care. Okay, and what happens next? The bromine just goes away. And so the carbon, hydroxide is going to stay, so where are these things going to go? Right now they're here. They're going to go up. So they went from down to up. So I think of this as an umbrella inverting itself. I think there's an umbrella in the wind. It used to look like this, and it's going to end looking like that. So let's draw that. I'm not bothered by the dipole right now. You can draw it if you want. Okay, so I drew the product by letting my umbrella invert. I didn't invent that idea. So instead of the tetrahedron facing down, sort of the tetrahedron's facing up. And then I tried to take this and rotate it around this axis by 180 degrees. So the OH that was on the bottom came to the top. The CH3 that was in the plane of the board, pointing at 10 o'clock or so, would end up in the plane of the board, pointing at 4 o'clock or so. Hi. So I just tried to rotate this picture this way. So the OH came up here from 6 to 12, and this went from 10 to 4, and this is coming out of the board, so it's going to be out of the board, but it's going to be over here. And this is behind the board, but it's going to be behind the board over here. So that would be rotation like it's a clock by 180 degrees. And then what I did, because I wanted it to look like my starting material, was I wanted to have the methyl on the left. And so I took this and I rotated it around this axis 180 degrees. So the methyl that's on the right went over to the left. This that was pointing, where Luke may have sat once upon a time, is now pointing to Mr. Syed's classroom. And this, which is pointing at the back stairs, is now pointing at Emma. Or me. It's pointing sort of more at me right this minute. But, Emma and I. So this is just this molecule re-envisioned. I imagine there's a way I could have done it in one step, but I am not super clever at this. Those are 3 drawings of the same molecule. I was just trying to get it oriented such that I could look at the ending material and look at the starting material and ask you, are they the same or different, or what's going on? What do you notice about them? So 1, bromine was substituted by hydroxyl. But 2, something else happened. Okay, he's saying mirror. We have a chiral center and we have the opposite chirality. Like we have flipped these 2 things. We have inverted the stereo center. We're going to talk about isomers today. How many products did we get from this? These are all one product. I just drew it 3 different times because I was trying to make sure that you could see that we reflected this through a mirror or we flipped these two. This is the other molecule. This is, that guy's enantiomer where the bromine and the hydroxyl have split.
Wait, so because we added the OH, it became the other molecule?
Because of the mechanism here, right?
Uh-huh.
Because we have to take that umbrella that used to face like this and make it face like this. We inverted that center. And in so doing, we have the opposite stereochemistry. So this molecule is handed, and that molecule is handed, and they have opposite hands. The problem is that when we name these, we use all sorts of rules, and you don't need to know the rules for IB. You just need to see that they're different, and so I'm not trying to belabor if this is D or L or R or S or plus or minus, because we have lots of different nomenclature schemes, and it's not interesting. I just want you to see that this molecule and that molecule are the opposites. So now I want to take 2-bromobutane. Is that a primary, secondary, or tertiary haloalkane? It's secondary. Because it's secondary, you can actually do SN1 or SN2. I started with SN2 because that's the interesting one for me right now. But I'd like to try SN1 instead. How is SN1 different from SN2? That's right. We're going to have an intermediate. We're going to have 2 steps. It's going to be faster. It's going to prefer protic solvents.
So what we did was just SN1.
What we did was just SN2. We are now doing SN1.
Okay.
So in SN1, in the first step, the bromine leaves. That makes a carbocation. The carbocation has 3 things attached. It has a methyl, it has an ethyl, and it has a hydrogen. What is the shape of that with 3 things around it? I would feel better if I changed it. Yes, you're right. Oh, I don't care. Do you get, yes, trigonal planar, yes. Are you happy with what I drew? No?
That's okay.
It's okay? So let me try to draw something that might be more pleasing. I think it would probably be better if I put the CH3 here, the H here, and the C2H5 here. Is that more reasonable? So that's this molecule just kind of. That molecule has a mirror plane. Anything with a mirror plane, because Brecken said that, is not chiral. That molecule is also not chiral because it has a carbon attached to 3 different things, not 4 different things. Not chiral. This. Carbon is not attached to 4 different groups, therefore it is not chiral. That molecule is planar. So now I'm a hydroxide, and I'm looking at this juicy cation. Because I have a negative charge and it has a positive charge, and I'm into it. We attract. It looks like this. It's planar. You're a hydroxide. You wanted this thing. How are you going to approach? The bottom or the top? Do you have any preference on a planar molecule between the bottom and the top? You can't hardly tell them apart. And so my expectation is that the hydroxide could come in from here or from there. Now when the hydroxide comes in to this planar molecule, it's going to have to bend these things away from the hydroxide to make that tetrahedron. So if the hydroxide comes in from the top, they'll bend down. And if the hydroxide comes in from the bottom, they'll bend up. But we'll end up with a tetrahedron. So I'm going to take this and I'm going to rotate it by 180 degrees so you feel like it's planar. So there's going to be the C. I'm going to throw this pen away. It's done in surface to us. There are videos where you can like put a string somehow and then like flip them around and try to get some ink into this. I feel like that's a level of service I'm unwilling to provide. How does that look? As a planar molecule, I'm just trying to show you edge on what this might look like. Maybe that even matches up better to that picture. And so I heard that I could attack this from the bottom or the top. And so I'm going to draw those two products. I'm going to have a carbon being attacked from the bottom. And I'm going to have a carbon being attacked from the top. That's correct. Just to make sure that we can look at this and see the relationship I'm aiming for, I'm going to take this molecule, I'm going to flip it 180 degrees. So I'm going to flip it around this axis by 180 degrees. Do wish this were easier to do. If Emma liked me more, I'd high five her, but she's busy writing. We killed it. How are these two molecules related? They have opposite chirality. We made both enantiomers. These two molecules are mirror images of each other. These two molecules are referred to as enantiomers.
Wait.
In SN2, we made a singular product. We made this product. In SN1, we made two products, a 50-50 mixture of this product and that product. SN2, yes, you can do an IA on this. You can use a polarimeter like Margaret to try to figure this out.
Which two are in?
These two molecules that are non-superimposable mirror images are enantiomers of each other.
Non-superimposable.
Why not the first? Is that first one just the
The
second?
first one and this one are the same. This is just two ways of drawing it. I'm just trying to show you that we flipped two of the things so it was easier to compare them. Just trying to make it better for you. So I'm going to write a culminating idea. SN2 is stereoselective. If we substitute a halogen on an isomer, a stereoisomer, a chiral molecule, we get one product. So stereoselective is the fancy word. It's not just selective. I'm telling you how it's selective. Stereo is going to be a word that I use to describe this whole notion of chirality. We're going to be talking about it all of today. And what's special about it is when you replace the halogen on a chiral molecule using SN2, you get one product. By difference, SN1 is not. You get two products. What is the ratio of the two products? And just because of our love of biology, biologists, we like to make up words that you have to memorize. We call that a racemic mixture. A racemic mixture is a mixture of the two mirror image molecules. An equal mixture.
So I have a question about this. So when you look at SN1, those two, like the new products that you redrew, where did they come from SN1?
Yes.
Those two came from SN1.
So from SN1, because we could attack this planar molecule from the bottom, ow, and get this. Or from the top, and get this. We got equal amounts of both products. I tried to draw them with the OH up so we could compare them and just see that they're different. So because we can attack from the top or bottom, we got two products. And we refer to those two products as enantiomers, and because it's an equal number of both, we call it racemic. So that's some vocabulary we'll keep working on. For SN2, because we're always gonna do backside attack, we get 100% inversion around that stereocenter. We only get one product.
What about the one on the left that's not circle?
So when the OH came in from the bottom, this is what I got. And I just wanted to reorient it so the OH was at the top so that all of the molecules were trying to look the same so we could identify what was the same and what was different. Because it's hard for me. It's hard for me to look at these molecules in 2D that are 3D, so I was just trying to rearrange them to make them pretty.
Is opposite chirality, like,
Is opposite chirality.
Is it just like the specific two parts that are opposite, or is it like global? Like when you say that they have opposite chirality, is it global?
I'm talking about around a singular chiral center.
Okay,
So
the chiral.
we're gonna have like some problems with sugars. So we're gonna learn words like diastereomer. You're gonna regret it. Trigonal planar. So your body is an excellent example of handedness because not only do you have hands, but you also have feet that behave the same way. Your feet are mirror images of each other. Yes? They are not superimposable. You have a big toe and a little toe, and if you put them on top of each other, you have big toes on either side. Like it's the same as your thumbs. It's just disgusting if I show you my feet. Right? Like no one needs that in their life.
You're not a feet person.
Not a, no. No. I'll wear sandals, I'm not there, but no. Feet are not beautiful, feet are pedestrian, usable. If I took Mohab and I sawed off both of his hands and both of his feet and swapped them and sewed them back on,
You'd be arrested.
I would be arrested. But strangely enough, old Mohab and new Mohab would be mirror images. But if we only swapped his feet and not his hands, it wouldn't work. It is true. So I feel, Rami, that's the question you're coming to. And sugars, like Mohab, have multiple chiral centers. So we'll have a fancy word enantiomer when they are mirror images of each other, and we'll have the goofy word diastereomer when they are non-superimposable, non-mirror images, because there are multiple chiral centers. But we're not there yet. We're not there yet.
We're not there yet, or we'll never get.
Oh, we're getting there, sweetheart, but just not
Today?
now.
We're getting there today?
We're in chapter 20, that's in chapter B, so I don't mind foreshadowing.
Chapter B,
Chapter B,
option.
the option, there's a unit on carbohydrates. Carbohydrates are sugars.
Is our option B?
B, as in badass. That was the mug I had yesterday. In my experience, the biologists benefit from biochemistry, and the physicists don't suffer. If I try to do the materials, the physicists suffer and the biologists suffer.
Did Andre told you how like you use chemistry in one of the bio questions, like the Calvin cycle? And
No.
like I use it too. Like it was like a question from Calvin cycle, like the first part. And then I forgot what it is. Like I remember exactly the chemical equation. I didn't know the name of the thing. And like I said, Dave, which one is the carbosylation? I was like, carbosylation adding a carbon. So I was like, yeah.
help each other.
Oh, you're talking about the paper
Huh?
one.
What's my question?
Yeah, for this test.
No, it wasn't this class.
It was on the paper
Oh,
one.
yeah, the first one.
That's
That was
good.
it.
Yeah.
Okay, so I gave you an example of this new type of isomerism, which is stereoisomerism. It's important with SN1 and SN2, so that's supposed to be a friendly review of SN1 and SN2. But now I want to back up and talk about all the wonderful different types of isomers. Do you remember how I introduced functional groups? The partners.
Oh. Well, that's not the word. You mean like how?
That worksheet?
How we,
Not the worksheet, not the graphing.
It was like, you had two groups and you separated them, and then there was like one that
Oh,
was
internal
inside
and
one. Yeah.
Yeah, I really feel that. So that's a type of isomerism, and that's a type you've seen before. That's when you have different connections. And generally speaking, that's referred to as structural isomers. And Raimi pointed out my favorite set, that's gonna be like the alcohols and the ethers.
Yeah.
Or the carboxylic acids and the which ones? I've forgotten. Which is it? What is it? Sorry, the coups and the kooks.
It's like a BT.
How about the chos? The aldehydes and the who? I don't love that. Ketones.
I didn't even have to look at my very recipe.
Okay, so those are my favorite type of structural isomers, and unsurprisingly, we call these functional group isomers. So do you agree with the statement that the connections are different? So what do I mean by connections?
Like, where's, so like for example, the alcohol is where the oxygen.
Where the oxygen is, what is bonded to what?
Yeah.
Yeah. So when we get to chapter 11 and 21, we do those together. This is money. Like being able to do this is good. Good. Will make your life better. Another set that we would have here is, you might remember when you did nomenclature that you had to talk about how this molecule would be different from this molecule. Those have the same functional group. They're both alcohols. How would I name them? Okay, I have a secondary alcohol and a primary alcohol. I like that. What is the name of alcohol number 1? Propanol, and alcohol number 2 is propanol. So these are called positional isomers. And sometimes I'm not going to fool with the functionality. Sometimes I could leave the functionality alone, and I could just change the backbone. I'm over the hydrogens like Raimi. I'm not changing where a functional group is. I'm not changing what the functional group is. I'm changing the branching of the carbon, and we call these skeletal isomers. So I'm changing that backbone. You feel okay about structural isomers? I feel like this is vocabulary. These are all structural because we're changed the connectivity. In one case, when we changed the connectivity, we changed the functional group. In one case, we changed where the functional group was, and in one case, we changed how the backbone looked. Is it a straight chain or is it branched? So which of these would have the same chemical properties? Go, Carter, go. She just points today. I would suggest that the alcohols and perhaps the branching should have the same chemical properties. So I think she was pointing right about here to say the 2 on the right are likely to have the same chemical properties. How about physical properties? You might think positional because we have molecules that are approximately the same size, but we are changing the shape of them. And so when we change the shape, we're going from something that's super stretched out, spaghetti, to something that's a little bit more spherical. I like orecchietti, but you know, it's more fun when I have someone who speaks Italian in here. And we talked about the difference in intermolecular forces. Which one has stronger intermolecular forces, the long, skinny spaghetti or the little tiny penne? The little tiny penne has weaker intermolecular forces because it has less surface area.
But does it have
Yes?
intra?
What? I just can't hear you. You're talking very quiet today, Raimi. You are not a quiet human.
Okay, so like, how does that do with the smaller, right, from the inside? Like, vertically,
I'm not blowing it apart when I'm boiling it, sweet Raimi. I am separating them. So the question is, if you were to like stand like this and hug Margaret, versus if you were to get into the fetal position and sit next to Margaret, in which case would it be easier for me to separate you two? When you are a tight little ball, no surface contact with each other, I'm just gonna pick you up and carry you away from her.
When we talked about physical properties, we also talked about
That's right, so here we have nothing to say about bond length. All these bonds should be the same length. The bond energies should be approximately the same. It's just in terms of how I'm reacting to the molecule next to me. So it must be the other half of this giant flow chart that's going to be interesting, because it's going to be kind of new. And the other side of this is going to be called stereoisomers. And what's going to make it a stereoisomer is that they have the same connections. The easiest kind of these are why these are in my room. Ethan Morgan was disappointed that I kept talking about it, but no kids knew what they were. So this is a molecule, and now I'm going to do this to it. This is considered a conformational isomer.
Can you do that again, but
Take two.
So, take two. Conformational isomer is when you just rotate around a sigma bond. So it's just making this molecule into a different shape. So when we took Raimi and she was stretched out ready to hug Margaret versus when she was in a little ball, she's still a Raimi, but we do refer to those as structural, as configurational isomers. Oh God. Don't refer to it that way. I knew it was wrong, it was coming out my mouth, but we're not gonna get it wrong. Conformational isomers, because it's like conformation in dogs. Like if you ever found yourself presenting at the dog show, you want to make sure your dog has got the right conformation, so your dog has to be standing just perfectly. You're not changing anything about your dog, you're just moving the dog around so his chin is at the right height and his back is sloping. Conformation.
Is it like an enzyme's conformational change where you just change the structure of it?
You like, so when something would bind to the allosteric site and the enzyme would change its active site, yes, that's a conformational change. Love it. Totally using that tomorrow. So when I scoot that around, I'm just changing the shape of it. I'm not changing anything interesting about it. You can recall early days of alkanes that we talked about what things might look like. This is your first homework in 3 dimensions. And if I had dichloroethane, 1,2-dichloroethane, we talked about how you could put an eyeball here and look at it and consider that you would see a chlorine up in front and 2 hydrogens down. You wouldn't see that, sorry. And a chlorine up and back and 2 hydrogens down. Remember what we called that conformation? That's right, we called this eclipsed. And then I could rotate around that 180 degrees and draw this. And so then we would get the staggered. And 180 And we said that there might be some different energetics. So it might be true that the molecule on average spends a little more time in this position than that position. And we might be able to draw some sort of potential energy that shows like when they're at 0, things are really bad. And when they're at 180 or pi, they're really good. But at 60, I don't know. I don't want to draw it. Like you get some sort of sinusoidal function and you could write a math IA, but y'all already have math IA topics. But like that's a sinusoidal function kind of thing. That's why people talk about conformation. What?
I don't give back that.
That's what I'm trying to do too.
Yeah.
No, you can. Doesn't matter.
I've never seen them ask me a question about conformational isomers. And you know I regularly get it wrong with the word because the other word is configurational. I wish they made those two words different from each other.
So there's only 2 in the stereoisomers, or is
Oh no, we're gonna keep going on configurational.
Distant water.
We have none.
Huh?
It's on the order list, we have none.
So,
You said we're gonna keep going on.
This side I'm gonna keep branching.
Okay, but it's okay.
So conformational, I'm done. Conformational, I'm gonna draw this picture. So you remember this is just like the orientation around a sigma bond.
staggered? And the one that Chiba was like from one was.
Yes, staggered and enclosed. I do staggered because it's my favorite.
And it puts it, it's like.
Yeah. And again, I've never seen a question, but I know it's in the book, so maybe you guys are gonna be the lucky people. But I don't expect anything. I also don't think, aside from having to remember vocabulary, it's a very difficult concept, like things rotate. But configurational isomers are gonna get exciting. We're gonna split them off into at least 2 categories. I already forgot what I'm supposed to ask as the question. Is it due to restricted rotation? The answer to that question is yes, if I'm over here. Not gonna put a question mark, I've answered the question, we're going to the left. And you guys have seen this before. If you took this molecule, it is different from this molecule. Just as you have seen cis and trans fats in the news. When we have that double bond, if the 2 chlorines are on the same side, cis, like cisgender, we call it cis. And when they are on opposite sides, we call it trans. Cis, trans. Why can't this freely rotate? Why are we on the can't just rotate side?
The double one.
Because of the double bond. Remember, the double bond is because I have 2 p orbitals sticking out of the board doing side-to-side overlap. If I want to rotate my cis into trans, I have to break I have to take that bond that I've made and I have to break it. So I have to break that bond so we have restricted rotation and then I can reform it. But it's going to take energy to break that pi bond. And so you can actually have, margarine, which is a trans fat, in the supermarket, and it will not convert back to a cis fat. You can actually have olive oil, which is a cis fat, and it will stay olive oil forever. It will not spontaneously become a trans fat. So cis and trans. Unfortunately, chemistry is hard, but Brecken speaks German.
You do?
Jawohl! If I could have had Morgan and Brecken going, that'd be great. So cis means that you have 2 things on the same side. implies the other things are probably hydrogen, or at least the same. But things could be more complicated. What would we do if we made this molecule because of that double bond, rotation is restricted. And so this molecule is not the same as that molecule. They do not freely interconvert, but I need a name to write down what this is. And the way I'm going to do that is I'm going to look at the carbon on the left, and I'm going to circle the thing attached to the carbon with the bigger molecular mass. I think it's actually atomic number. They'd be the same except for like argon and potassium are in backwards order. There shouldn't be a difference. But I think strictly speaking, it's atomic number. And so iodine has a bigger atomic number than bromine. Chlorine has a bigger atomic number than fluorine, and those things haven't changed, but their locations have. When they are on the same side, I do not refer to it as cis anymore. I refer to it as together. Oh, Deutsch.
Zusammen.
Zusammen. I don't know how to spell it either. We use a capital Z. It means together. In German.
Wait, so those two.
Thank God we don't use Vietnamese for nothing here.
So those two molecules are susammen.
This singular molecule
Uh-huh.
would be the Z version of the molecule.
Uh-huh.
That molecule over there is a different molecule, so we're going to quiz Brecken on the word apart. Starts with the E.
So the ones with like the bigger mass, when they're on the same side, it's like the Z, and then, okay.
Yes, and when they're on this different sides, we call them apart, which in German is signified by the capital letter E.
How was the second word pronounced?
Entgegen. For me, because I don't speak German very well, outside of like indeed and a couple words, that's what jawohl means. Together and zusammen both start with consonants, and apart and entgegen both start with vowels. So when I see E, I know they're apart, and when I see Z, I know they're together. So what would this look like if we had more carbons in our life? This time I decided to choose a molecule that I don't mind naming because I decided not to be crazy all the time. I hope you see that this is a 1, 2, 3, 4, 5 long chain with an ene in it at position 2. And I hope you see at position 1, 2, 3, there's a methyl. Unfortunately, Emma and I were unsure as to whether we wanted the methyl group and the hydrogen to be as they were before or like this. Both of those molecules have the same name. Here. I still have a chain that's 5 long, a double bond at the second position, and a methyl coming off of 3. So what I need to do is I need to identify the thing with the highest atomic number that is attached to each carbon. Here it's easy. Carbon is number 6, hydrogen is number 1, but there it is not so easy because it is carbon for both of them. So then I'm going to take the sum of the things that the carbon is attached to. Here's it's attached to 3, here it's attached to 2 plus 6 is 8. molecule there, is it N-gigan or zusammen? UZ. So that is how we would call that molecule. That's not a big deal. So cis and trans, I think you've seen. And this is just a step apart when we have like 3 things attached to this double bond instead of just 2. There's another tricky case that Ramey's going to miss, so you're all going to tell her about it. When rotational action is not allowed. And that's when you have a molecule that has a ring in it. Do you ever feel like you're going to fail? That's gross. Can I?
Yes.
Where does it go?
I mean, we won't know what's right now.
Here, we're gonna try 2. You're trying to draw cyclobutane. Artistically, you're trying to draw it artistically. That one's gonna go there and there. That one's gonna go there and there. I don't hate it. That one's gonna go there and there. This one's now the hard one. I don't hate it. I would like that to be angled down. Okay, it's as good as it's gonna be. If you hate my picture, that's okay. Think you'll enjoy drawing it for yourself on the homework. But that's what I tried to draw. And within reason. Didn't suck too hard. But there are 4 hydrogen atoms that are kind of on top of this molecule and 4 hydrogen atoms that are a bit more on the bottom of this molecule. And so I tried to have 1, 2, 3, 4 that kind of look like they're on top and 1, 2, 3, 4 that kind of look like they're on the bottom. But now I'm going to swap out 2 hydrogens for, you know, what hopefully looks like chlorine to you if you have a vivid imagination. So the 2 pink things are now something different. And so this molecule would be 1,2-dichlorocyclobutane. 1,2-dichlorocyclobutane. But what I've done with these 2 chlorines is I put them on the same side of the molecule. If Emma, because she's ever a critic, was like, I don't like it, I want this, we still would refer to it as 1,2-dichlorocyclobutane. I can't rotate my way out of this even though everything's a single bond because now I have a ring. The ring is a barrier to rotation. To rotate this, I have to like break a bond and rotate it and make a new bond. It's really quite hard, honestly. When they're on the same side, we call them cis, and when they're on opposite sides, we call them trans. So this is not hard in terms of nomenclature. It's just, I don't think it's obvious without being directly told that rings prevent rotation. I would not have gotten there. So the double bond I understand because of the pi bond, because I need the side-to-side overlap of p orbitals, and if I start rotating, I break it. The ring, like, it just wouldn't have crossed my mind that someone would ask the question, let alone that I could know the answer to it. But they did, and we can. And so what I'm going to put here is due to restricted rotation, double bond, or ring. And I'm going to put cis-trans. And I'm going to put EZ. And I hope you feel okay. Yeah, I feel it. here, we have the last box. We refer to these guys as optical isomers. In the old days, we referred to those as geometric, but that word seems to have died. I don't know why. And optical isomers come in two flavors. They come in the flavor, are they mirror images? In which case we describe them as enantiomers. Or they are not mirror images. We refer to them as diastereomers. Diastereomers. Like diametrically opposed or diameter. So these optical isomers are going to occur when we have chiral carbons. These optical isomers are going to occur when we have 4 different groups attached to the same carbon. In paper 2, on the core of the gloriousness that is IB chemistry, no nomenclature is required for enantiomers and diastereomers. In paper 3 of the gloriousness that is IB chemistry, nomenclature, like we need to learn how to call them.
How long has it been since like people have taken
It will be 3 years. 2 years did not have it, so it was.
We have it, right?
You have it. That's why we talk about it all the time. Try to take the pressure off the next semester, right? Like if I can do a little bit today that I don't have to do in March, or I can remind you of today, in March. Like remember when we talked about this?
Second semester is gonna be better. Because I'm done with the college apps, most of it, and I'm easy. And I'm done with my IA for doing. I just have my IB exam. Right?
There's something that has to do with the first branch of the configuration.
Sorry.
Like, I don't know.
It's the one that with the double bond rings.
So what was it called?
So in the old days, they used to be called geometric isomers. But in 2016, the IB deleted that term and only uses the word configurational isomer. And then they go on to talk about these guys further as optical isomers. I can't defend it. The 2 optical isomers are called enantiomers and diastereomers. As far as I know, the world does, just the IB don't.
So if we answered geometric isomer,
I don't think you'll have I don't think you'll be asked a question. I hope you won't be asked a question. Is that molecule chiral? How did you know? 4 different groups attached to the carbon. So sometimes you'll actually see this with a little star on it. Common IB question is, hey, open your data booklet, circle the molecules that are chiral. So there's drugs in there for option D, there's vitamins in there for option B. Like why don't you take a look at vitamin C and say, hey, is that chiral? And all you're doing is looking at the carbons and saying, are you bonded to 4 different things? But you might wonder why I care so much about this handedness, because it doesn't seem like it's very important. Like I know it's important in drug design. Did we talk penicillin?
yeah. Oh, yeah, no, it was the
Thalidomide?
baby drugs, the baby drugs.
Okay, so thalidomide is one story. The other story is penicillin. So every amino acid in your body has the same stereochemistry. So all of the amino acids have this general shape. And so all of them except for glycine are chiral. Why isn't glycine chiral?
I didn't feel like I
Because it doesn't have 4 different groups. That's glycine. It has 2 hydrogens. Margaret says that's not 4 different things. It's dead to me, but every other one has something interesting, like that's alanine. Is that reasonable? Now we have 4 different groups. Every one in your body is L, levulo, left oriented. But like, why do I keep using the words left and right? I think part of it is because I understand it in terms of my hands, but part of it is also because of what these molecules do. What do you know about light? Oh, photons, that's so hard. Oh, I like waves. I'm in a wave kind of mood today. And so what I want to picture is that I have light. And light is all going, from me to Audrey. And so when the light is going from me to Audrey, what we can do is we can plane polarize that light. To plane polarize it means to pass it through a filter such that all of the light has the electric field, this way. We could polarize it a different way and make the light point that way as it's traveling. So light is a wave, it's a traveling wave, right? And so we draw it like that, yes? What is oscillating here? Energy is constant, it's light of some frequency. I believe there's an electric field and a magnetic field or something in light. Have you ever been to a 3D movie?
Yes.
Okay, great. So can you imagine the goggles, the glasses that you wear?
Yeah.
Have you ever played with them at all? What happens if you take your glasses and your friend's glasses and put them on top of each other so the right and the left glasses overlap? They turn dark. No light comes through. It's because what they've done is they've taken the light and they've made it so the light is only coming at you in 2 directions. The light is actually going this way or this way. And one eye glass can see this light, and the other eyeglass can see this light. But if we put these 2 things on top of each other, we see no light. And if we take our glasses off, we see both lights. So you take the movie off, it's all blurry. Right? Like in real life, it's all blurry. That was funny. You'll laugh later. So what we're going to do is we're going to take light and we're going to make it all look like this. We actually pass it through one eyeball of 3D glasses. Okay? So all of the light is pointed this way. So it's going toward Audrey, but it's all behaving very nicely, and we call this plane polarized. Plane polarized, like polarized glasses. You guys all must have polarized sunglasses. You guys are fancy people. You're fancy, you have polarized, but you don't even know it. You're so fancy. You're just like, yeah, those are just the glasses I got.
What are polarized sunglasses?
They're supposed to reduce glare, but that's because they only let in some polarization of light. They only let light in that has a particular axis. This conversation is going really poorly. All the physicists are clearly in the other class.
Yeah, Quinn's not
Where's Lynn?
Quinn is in the University of Rochester, along the Genesee River, learning why in lacrosse we do West Jennies.
What does that mean?
It's a drill in lacrosse named after Rochester.
How is the West Jenny? West?
I don't know.
He was already gone.
Yes, he was in Trinidad fixing his visa, and now he's on a college visit, and he just kind of low-key giggled because he is missing his 3rd cross-country meet in a row, if not his 4th, and his 3rd week of school in a row, if not 4th. Quinn is living his best life.
I'll take it 3.
Yeah, do you want it? Okay. Yeah, there's the electric field and the magnetic field, and we are polarizing the light, making sure it moves in the same way. Imagine that you just have super skinny little lines, so the light that is not phasing up and down will pass through. That's what a diffraction grating is. and trans anymore because they don't have two things and two hydrogens. So when molecules become more complicated and cis and trans aren't adequate, I have to start using E and Z. So it would be possible to call all trans molecules E molecules and all cis molecules Z molecules, but traditionally we don't do that.
But didn't you say they weren't true cis and trans because they don't have like outside?
Rectangle and
All trans molecules are E. All E molecules cannot be described as trans.
that
The
circle square thing.
I'm trying to draw a Venn diagram.
Rectangle square thing. Rectangle square thing.
Okay, so I pass light through a polarization filter or a diffraction grating such that I only see light that is polarized in one direction. I then have a glass tube. Inside that glass tube, perhaps I have a 5% solution of glucose. Perhaps not. Glucose is a chiral molecule. What?
you just like eat glucose by itself.
You sure can. If you have the diabetes, you can buy glucose tablets if your blood sugar gets low. I mean, you can buy them if you don't have diabetes, but glucose doesn't taste good.
Doesn't?
Glucose is not very sweet. Sucrose is much sweeter than glucose.
What about fructose?
What?
What about fructose?
Fructose is also less sweet than sucrose.
But is it sweeter than glucose?
I don't know. I assume so.
Can we try it?
We're not just eating on taste test.
What happens when we pass light through a chiral molecule like glucose, or an optically active molecule, or a molecule with optical isomers, is that the light will rotate. Said differently, chiral molecules rotate plane polarized light. Chiral molecules rotate plane polarized light. And what's cool about them, among many things, is if Mohab took the right-handed molecule, it would rotate light 15 degrees, say to the right. If Audrey took the left-handed molecule, its enantiomer, its buddy, it would rotate light 15 degrees to the left. So if Sophia took a racemic mixture of the right hands and the left hands, the light would stay straight. The light would not change. So, if Amarachi did an SN1 reaction, what would happen to the light? It would stay the same because we make both enantiomers. But if Emma did an SN2 reaction, she's going to get a chiral product and it's going to rotate plane polarized light. So it would be possible to measure the relative amounts of SN1 and SN2 in a secondary haloalkane by monitoring the rotation of plane polarized light and changing, say, the solvent. See, polar protic solvents are better for SN1 and polar aprotic solvents are better for SN2. So you would expect that there would be more rotation of light if we did polar aprotic solvents.
So this is pertaining to optical isomers.
So this is all about optical isomers. So this device is called a polarimeter. A polarimeter measures the number of degrees by which the light has been rotated. The light is rotated by a chiral molecule, or a stereoactive molecule, or an optically active molecule. I don't know. Polarimeter. Is this miserable?
I'm just.
Yeah, that's why I put 5% glucose in there. Yeah, it's cool.
I'm just.
So SN1, same thing, same like in terms of
The SN1 would not rotate it because you get the racemic mixture.
because you have both
Both hands.
SN2 you only have one.
if you start with something chiral, you will end up with something chiral. Whereas SN1, if you start with something chiral, you will end up with something that is achiral because you will have equal amounts of both hands. That's what I had in mind for today. Yeah.
So like,
I mean, I had homework, but I didn't photocopy it because I was so in love with the math class and I really wanted to teach it.
you were saying earlier that by measuring like the angle at which it turns, you can find out what?
You can find out like the relative amounts of SN1 and SN2. I think it's a pretty hard experiment to do in the classroom, but I think logically it makes sense that it would be a way to discriminate. Because one makes a chiral product and one makes equal amounts of both, so it shouldn't rotate them.
The angle at which it turns, how much of SN1 and SN2 is it? Because like, if it like turns a lot, then there's a lot of SN1.
So if you had a secondary haloalkane, like bromobutane, we know that molecule is chiral. But if that molecule only did SN1, the product, the 2-butanol, would appear in both chiralities, in both handedness, in both enantiomers. And so the light that went in would be the same as the light that went out. Because every time you had a molecule try to move it to the right, you would have a molecule try to move it to the left. But if that same molecule underwent SN2, then all of whatever it used to be would be converted into a particular chirality. You would only have right hands, and so now the light would move.
So this experiment works for SN2.
So it would be a way of deciding how much of your molecule did SN1 versus how much of it did SN2.
So like if it rotated a lot, so the SN2 was like the dominant.
Right.
This is not much.
Right, so, and you could do some sort of a calibration curve, so you could start with something that was full of product and see how much it rotated, and then do your experiment to see how much.
Why would a molecule undergo more SN2 than SN1 or like vice versa?
So we know that SN1 is faster, so we think that a secondary would do more SN1, but we also know there's a solvent effect. We know that protic solvents slow down SN1, and so SN2 would become more dominant. Protic solvents find the nucleophile and like bind it up, and in SN1 I need the nucleophile to be able to attack. In SN2 I need the nucleophile to be able to attack. In SN2 because it's the concerted process. Sorry. Yes.
Is that the end of the lecture?
A homework that I'm going to print out for you.